Hello, and welcome to the Mathematicians Podcast, the podcast where we follow the fascinating stories behind the people that count in the history of mathematics. I'm your host, Benjamin Cornish, and today we're diving into the life and works of a man who was so ahead of his time, he practically put the Earth into Eratosthenes. Oh, that doesn't work. But that's right, we are doing Eratosthenes of Cyrene. A man whose genius stretched from mathematics to geography, to poetry, to philosophy, from ancient Alexandria to my classroom of year 7s. I used to have a friend who was a pirate, and one day he decided to take me paddleboarding. For those of you who don't know, this is a sport for people who enjoy swimming but do not enjoy knowing exactly when they will go swimming. The goal is to stand up on a large floating board and pretend to enjoy yourself. On this trip, he took me to a nearby river. The wind was strong, heading downstream, but the river was gentle and slow. We spent about 55 minutes travelling upstream, and in that time managed to get about 500 metres upstream. Then, somewhat disappointingly, we only took 5 minutes to go downstream back to the start. I was frustrated that after an hour of paddling, we had only moved 500 metres there and back. And I said, shame we went so slow, we only averaged 1 kilometre per hour. And he said, Arr, ye be forgetting the river flow rate, she be travelling at 2 kilometres per hour. Thus, in the hour we be paddling, the river moved an additional 2 kilometres. So you get back to the start, we actually went at 3 kilometres per hour. The river was moving at 2 kilometres per hour, and we moved at 3 kilometres per hour. Well, then you could model the hour as us travelling at 1 kilometre per hour for X hours, followed by a negative velocity of 5 kilometres for 1 takeaway X hours to arrive back at the start. But then we have X takeaway 5 times 1 takeaway X, which is equal to 0. And that would suggest that X is equal to 50 minutes, when in reality it took us 55 minutes. So I thought about this for a moment, and I decided that the fluid flow of the river was less consequential than the tremendous wind that we were battling. We tested this by standing stationary, no paddling, and measured the velocity of us standing up on the board to be 5 kilometres per hour. Which means the wind, added to the additional 3 kilometres per hour of the river speed, gave us 5 kilometres per hour. So we agreed to assume that our efforts in paddling were constant in both directions, and we called this unknown velocity v, and then we solved for v, given that we now know that x is 55, and the combined river and wind speed should be 5. So that means 55 out of 60 times by v take away 5, subtract 5 out of 60 times by v plus 5 should equal 0. And that gives a constant velocity of 4 1/6 kilometres per hour. So which is correct for our speed? Were we slow and only moving 1 kilometres per hour on average? Did we manage to average 3 kilometres per hour? Or maybe it was 4 and a bit kilometres per hour at a constant rate? Well, I guess the answer is, it depends. Depends on what you're trying to say. Which is the classic teacher's way of saying, I don't really know. Before we jump into Eratosthenes' achievements, let's set the stage. This was the 3rd century BCE, a time when Alexandria in Egypt was the intellectual hub of the ancient world. The Library of Alexandria, not the place to borrow books, but the internet of its day, minus the cat memes and countless people producing self-indulgent podcasts. And Eratosthenes? Well, he was the chief librarian. We've talked a bit about the people who visited the library to study at the library. This guy was the library. Eratosthenes was a big picture thinker, but he also had a knack for the finer details. To most, he's best known today for measuring the circumference of the Earth to within a shocking accuracy. But as we'll discover, that's just the tip of the proverbial iceberg, or, given his methods, the tip of the sundial. To me, he is best known for his work on prime numbers. So who was this man, and what made him tick? And why should we care about a guy whose name is arguably harder to spell than Pythagoras? Let's find out. Eratosthenes was born around 276 BCE in Cyrene, a Greek city-state located in what is now modern-day Libya. Eratosthenes studied under some of the most brilliant minds of his era. He first trained in Athens, where he immersed himself in the teachings of philosophers like Zeno of Citium, the founder of Stoicism. Now, while Stoicism is all about suppressing your emotions, citation needed, I can't help but think Eratosthenes might have felt a little smug about how much he was learning, because he became a poet, an athlete, and an intellectual powerhouse. Eventually, his reputation caught the attention of none other than Ptolemy III, the ruler of Egypt. Ptolemy invited Eratosthenes to become the chief librarian of the Library of Alexandria. Imagine getting a job offer to be the head of Google of the ancient world. That's how big a deal this was. While in Alexandria, Eratosthenes earned the nickname Beta. At first glance, that might sound like an insult, like calling someone second best. But to the Greeks, Beta was a compliment. It meant that he was a master of many subjects, second only to specialists in each. Or as I like to think of it, the original jack of all trades and master of Beta. Before we dig into the maths, let's appreciate the Renaissance man side of Eratosthenes. He excelled in fields that would have made Da Vinci jealous. Eratosthenes is considered the father of geography. He was the first to use the term geography as the study of land, and wrote the 3-volume treatise of the subject. In it, he introduced a grid system of latitude and longitude to map the known world. This is where I might nod to my brother, who believes that the Earth is flat, as Eratosthenes was arguing that a 2-dimensional coordinate would be suitable for mapping the world. And as my brother likes to point out, you can tile your kitchen with square tiles, but not an orange, so your kitchen can't be orange-shaped. But what we see with Eratosthenes is an early suggestion of polar coordinate system, and a strong recognition that the Earth is a sphere, so much so that he went ahead and measured it. He also theorised that the Nile's annual flooding was caused by heavy rains upstream in Ethiopia. And this sounds obvious now, but back then, this kind of reasoning caused a groundswell. People were still blaming the floods on the gods being in a bad mood, or perhaps asking the gods to flood to bring fertility back to the banks of the Nile. Eratosthenes compiled a chronology of world history, establishing the dates of major events like the Trojan War. He was a historian. He even calculated the date of the first Olympic Games. That's right, he was literally timing history. I always used to find it funny that there were these historians that we learnt about in history lessons. Eratosthenes was trying to talk about historic events, but missed out on seeing what I think of as most of history. After all, he is only number 26 out of about 1,000 mathematicians I plan to discuss. Only as an adult did I start to come to terms with the idea that we might not be living in the end of days, and maybe people will once look back at us as anachronistic. Eratosthenes also wrote poetry and philosophical essays. Unfortunately, most of his work has been lost to time, but we know he had a sharp wit and wasn't afraid to criticise others. He once described his rival scholars as critics who could see the small faults in others while missing the great accomplishments. Now, let's get back to the maths. Eratosthenes is best remembered by mathematicians for his ingenious method of finding prime numbers, the Sieve of Eratosthenes. And no, this isn't a kitchen utensil. The sieve is a simple algorithm that systematically filters out composite numbers, leaving only primes. Here's how it works. Write down a list of all integers, starting from 2 up to some maximum number n. Start with the first prime, 2. Cross out every multiple of 2 thereafter on the list. Move to the next number that hasn't been crossed out, which in this case is 3. 3 must be a prime, so we're going to circle 3 and then cross out every multiple of 3 thereafter. At this point, we're not going to move to 4, because 4 was crossed out after we'd crossed out every second number. So we know that 4 is a multiple of 2, or a multiple of something at least, and therefore not prime. So the next number that hasn't been crossed out would be 5. And then we cross out every 5th number. And after that, we can skip over 6, because 6 has already been crossed out. So the next number is 7. So 7 must be a prime number. And we can carry on this process all the way up till we reach the nth number, and what we'll have left is all of the primes have been circled, and all of the other numbers have been filtered away. It's simple, it's elegant, and it's computationally efficient. In fact, modern computers still use variations of this method to find primes. So why does this matter? Well, primes are the building blocks of mathematics. They're fundamental to number theory, modern cryptography, and inspirational books about why maths is cool from the 1990s. You can even reproduce the Sieve of Eratosthenes as an actual sieve. If you start with a disk divided into two sections, you can cut one of these sections out, and then spin the disk so it completes one rotation in every 2 seconds. Then get another disk and divide it into 3 sections and cut out 2/3, and spin this on top of the first disk so that it completes one rotation every 3 seconds. Do the same thing with a disk that spins every 5 seconds with 4/5 cut, and again a disk with 7 seconds that has 6/7 cut out, and you can repeat this for as long as you have the patience. If you then spin all these disks simultaneously, remembering to spin them at different speeds, you can shine a light through the disks to reveal a pattern. Every nth second, the nth disk will block the light. Thus, when no light penetrates through all the disks, you know that the number of seconds passed will be divisible by something. Thus, at any time that light reaches through all the gaps in the disk, you have a new prime number. If the Sieve of Eratosthenes was his warm-up act, then his measurement of the Earth's circumference was his headliner. Here's the story. Eratosthenes had heard that on the summer solstice, in the town of Syene, modern-day Aswan in Egypt, the sun cast no shadow at noon. This meant that the sun was directly overhead. Nowadays we'd say that it exists on the equator. But meanwhile, in Alexandria, shadows were very much a thing. Cue the light bulb moment. Eratosthenes hypothesized that the difference in shadow angles between Syene and Alexandria could be used to calculate the Earth's circumference. Here's how he did it. He measured the angle of the shadow in Alexandria at noon on the solstice. It was about 7.2 degrees, or, as he would have said, roughly 1/50th of a circle. He knew the distance between Alexandria and Syene was approximately 5,000 stadia, a unit based on the length of one stadium. And then using simple proportions, you could say the angle divided by 360 is equal to the arc length divided by the circumference. And he calculated the Earth's circumference to be about 250,000 stadia. Modern scholars estimate that depending on the exact length of the stadion he used, Eratosthenes' measurement was accurate to within 1 to 10% of the true value. Flat earthers, take note. At this moment, I should point out, however, that the Earth doesn't actually have a circumference that we could measure using circular geometry. The reason being that the Earth isn't a sphere. In order to make use of the technique that Eratosthenes used, we'd have to assume that the circumference around the equator was equal to the circumference from pole to pole, one of the great circles, and that would suggest that the Earth is a sphere. But the Earth is not actually spherical. It's what you might call an oblate spheroid, or perhaps a 3D ellipse. That is, the line that goes around the equator has a larger circumference than any of the great circles that go through the poles. It's been squashed. One of the reasons for this is, as the Earth spins, the centripetal, or if you prefer, centrifugal forces are pulling at all of the mass of the Earth, trying to take it away from the centre. And the points at where the centrifugal forces are felt greatest is where the spin is greatest, and that is further away from the axes. So the forces pulling out are greater towards the centre, because at the centre it's further from the axes, and that pulls it into this squashed sphere shape. Eratosthenes' work paved the way for countless advancements. His method of calculating the Earth's circumference inspired later geographers, including Ptolemy, who built his grid system to create more detailed maps. This led to more inspiration for people to go off and test those maps out, international travel being a hallmark of the Islamic Golden Age. The Sieve of Eratosthenes continues to be a fundamental tool in mathematics. In an age where computers can process billions of calculations per second, his simple algorithm remains a testament to the power of elegant thinking. Even his approach to interdisciplinary learning feels modern. Today we talk about STEM, science, technology, engineering and mathematics, but Eratosthenes lived it. He showed that curiosity knows no boundaries, and that the connections between disciplines often lead to the most profound discoveries. As maths teachers, we're often asked to find the maths in other subject areas. And I think Eratosthenes is a great example of the maths of geography. But perhaps more importantly, he reminds us that any process of quantization, that is finding the value of something, should involve an element of mathematical inquiry. So what can we learn from Eratosthenes? First, that maths isn't just about numbers, it's about solving problems, understanding the world, and occasionally roasting your rivals. Second, that interdisciplinary thinking can lead to breakthroughs that change the course of history. And finally, that even a guy nicknamed Beta can achieve alpha-level greatness. Thank you for joining me today on this journey through the life and works of Eratosthenes. If you enjoyed this episode, don't forget to subscribe, leave a review and comment. Might feel silly, but these kind of engagement metrics really help the algorithms to share the pod to more people. And the more listeners and support I get, the more likely I am to continue another week before giving up and putting down my microphone. You can also join me on Blue Sky at Mathematicians-Pod, where I occasionally post things I find cool or other projects I'm working on. Speaking of other projects, last week I mentioned the maths chat show Unnatural Numbers, available on YouTube. What I perhaps didn't mention was that the purpose of this platform is to get new speakers into mathematical communication. I'm looking for students, young teachers, recent graduates considering a career in communication who would like to come onto the show and practice their public speaking skills. If you know someone who might find this enjoyable, then please share the link with them that's in the show notes and they can sign up and have a go. Alternatively, if you are already an experienced maths teacher, professor or communicator and would like to support this endeavour, I'm also looking for you to be a guest to help give the show some more gravitas and professionalism and help encourage a new cohort of speakers. So if you'd like to spend an hour having a chat with me and other enthusiastic mathematicians about numbers, get in touch. You'd be warmly welcome. Links in the show notes. Otherwise, join me next week, where we will be having unconditional fun with Chrysippus. If you tune in, then you will have a good time. Until then, goodbye. The music today is Dance Macabre Finale by Kevin MacLeod. You can find more information in the show notes.